this video, I'm going to be talking about how we can use a particular equation that we often call the sine rule. Now, essentially, this is just going to be substituting numbers into an equation. To see where the equation comes from and to understand how it works, you'll have to watch the next video on proving the sine rule. Today, I'm just going to state it, and we're just going to talk about how we can use it. So, use of the sine rule is all based on this triangle, which is the same triangle we used when talking about the area of a triangle. The idea is that we've labelled all three vertices with capital letters, and then the sides opposite those capital letters have the little letter versions. Opposite capital C, we've got a little c. Opposite capital A, we've got a little a. Opposite capital B, we've got a little b. Now, it doesn't matter what order we put these corners in, but once we've done that, it matters what the sides are, because the sides have to match. They have to be in pairs. Okay, so that's the triangle we're going to be basing it on. And once we have this triangle, we can say the following is true. Sine A over A is the same as sine B over B, which is the same as sine C over C. So here we've got, well, two equal signs, which is unusual, but that's only because we're saying there are three things that are exactly the same as each other. So if I already know what sine A over A is, then it's going to be the same as sine B over B, or sine C over C. Now underneath I've got this other version, which you sometimes see. Now this is actually the exact same idea, it's just I've flipped all the fractions, which we are fine to do, because if that ratio is equal to that ratio, then this ratio has to be equal to this ratio. All we've had to do is, well, times everything by A divided by sine A, and the same with B and sine B. Essentially though, we get this alternative version. Now the reason we have two versions is that it is really useful to have the unknown at the top of our fraction, to have it in the numerator, just because it makes our calculations a little bit easier. In theory, you could use either one of these and you would be fine every time, but as I say, we do prefer to have the unknown value on the numerator. Right, so this is the kind of question we get where the sine rule turns out to be useful. Now what's important here is that, including the unknown, the four things that I'm bothered about in this triangle are two pairs of the opposite things that we were talking about before. So here I've got this vertex and this length. Those two are opposite each other. And here I've got this vertex and this length, and those two are opposite each other. So that's the kind of situation where we start to think the sine rule is going to be useful to us, because we've got these pairs. Now the next thing I'm going to do is I'm going to label this triangle, and as I said, it doesn't matter how I do the corners, so I'm just going to put A, B, C. That's fine, doesn't make a difference. But then once I've done that, I need to very carefully make sure I put the lengths in the right place, because we have to have opposite pairs. Now, just based on the way that I've set this up, and I did put the letters in randomly, I'm not going to need the whole sine rule at any point. I'm only going to need part of the sine rule. So in this example, I've not used A at all. Can you see how I haven't been given any information about A, and I don't need to find anything about A. So I'm going to ignore the A part of the sine rule. I am just going to focus on sine B over B equals sine C over C. That's all I care about for now. And once I've got this, I'm just going to substitute my values in. So I've said that capital B is X, little b is 3, capital C is 43, and little c is 5. So I just substitute those numbers in, or in X in the case of that particular case. And this is an equation I can solve. So I'm going to times both sides by 3, which means that sine x is 0.41 approximately. And then I use the inverse sine and get 24.15. So both of those things are things I did on my calculator. So I've told you by the sine rule that this value here, this x, this angle is 24.15. Right, next one. So now I've got a slightly different arrangement. I am going to follow the same procedure though. So I'm going to first label my angles. Doesn't matter how I label them, as long as I'm using the capital letters. I'm then going to label my sides, which does matter because the little a needs to be opposite the big A, little b needs to be opposite the big B, and little c needs to be opposite the big C. I can see here that I've not used b this time, so I don't need the b part of the sine rule. I can ignore that and just use sine A over A equals sine C over C. And then I substitute my values in, so A is x, big A is x, little a is 6, big C is 43, little c is 5. Times both sides by 6. Plug that into a calculator, and then inverse sine, because sine of x is 0.82, which means that I need to inverse sine to get x on its own. That's 54.92. Okay, I've slightly moved my triangle around, but that doesn't matter. What's lovely about the sine rule is that this will work for any triangle. No matter the orientation or the side length or anything, this will just work. So I can see, crucially, the reason I know sine rule is going to help me is because I've got two sets of opposite pairs. I'm going to label my triangle, ABC. Carefully label the side lengths, ABC, making sure we've got opposite pairs. I can see that again I haven't used B at all, so I'm going to use the A and the C parts of the sine rule. Sine A over A is sine C over C. Capital A is 71. Little a is 7. Capital C is X, and little c is 5. Now I notice that these two are the wrong way around, but it doesn't make the slightest bit of difference to what we're doing. So if I know that that's true, I can times both sides by 5, get that sine x is 5 times sine of 71 over 7, which is approximately 0.68. And then I inverse sine and get 42.48. Now, that's how we can find angles, which is one of the uses of the sine rule. But as long as it's only one unknown, we can have a slightly different setup. So in this question, it's an unknown length I've got, but I still have these two pairs. So I still have a corner and an opposite side, and I have a corner and an opposite side. So I still have these two pairs. So I can still use the sine rule. I can label the three corners, A, B, C, then carefully label the side lengths, and I could use this formula. However, my problem is that here we've got little a, that's going to be in the denominator. And as I said at the beginning, that's not ideal. It's fine, it would work out. The answer would pop out, it would be fine. But it's slightly easier to use this version of the sine rule, just so that my x is on the numerator. Okay, so I've got this version now. I'm going to substitute in. So little a is x, big A is 27, little c is 5, and big C is 43. I can then times both sides by sine of 27 and type that into a calculator. Sorry. Now what you'll notice here is that we didn't have to do any inverse sining because we were finding a side length this time, not an angle. So if anything, slightly easier. This length here should be 3.33 centimeters. Another example. Again, I've got two pairs here. So I've got a corner and an opposite side and a corner and an opposite side. I am going to label all of my vertices and the opposite side lengths. And I can see that I haven't used C, so I'm going to ignore I should ignore the C part. I'm now looking ahead at my slide. I've actually labelled these C. These should be B, little b and capital B. Never mind. Doesn't make a lot of difference. Because I'm still going to do essentially the same thing. I'm going to put in little x over sine of 43 and 5 over sine of 27. I can times both sides by sine of 43, type that into a calculator, and I get 7.51. Okay, final example. Again, I've got these two sets of pairs, these two pairs of opposite things. I'm going to label all my vertices, A, B, C. I'm going to carefully label the side lengths so that we've got these matching pairs. Big C, little c, big B, big A, little a. Now I'm not using a in this case, so I'm going to ignore the a part of the sine rule and just have b over sine b equals c over sine c. Little b is x, big B is 27, little c is 5, and big C is 27. So we get that x over 20 sine of 27 is the same as 5 over sine of 27. Times both sides by sine of 27, then type that into a calculator. And I get 5. Now, of course, that shouldn't have been a surprising answer, because clearly we've got matching angles here. This must have been an isosceles triangle. So again, just a quick reminder that sometimes the sine rule is overkill, but it would still work. I could have just worked this out using year 6 maths to notice that this is the same as that side. But the sine rule gave us the same answer, so that's good. Right, the key points from this video. We can use the sine rule to find missing angles or side lengths of triangles. In theory, we can use the sine rule with any triangle. It is not restricted to, say, right angle triangles. It does work for any triangle. We would use the sine rule if we are considering sets of opposite side angle pairs.